Welcome everyone to Iron Beetle, a show where we, I think at this point for more than a year, every week at 5 p.m. UTC on Friday, come together and read some of the code of Beetle database. Because Beetle is pretty exciting database. It is quite unusual. It doesn't have SQL. It's implemented in Zig. It doesn't allocate memory. After startup, what else? It is fully deterministic, and in general is pretty exciting code base to study. And today is a very special day. Today is January the 2nd, 2025. So we as humanity made it. We've made it past the first quarter of the first century of the third millennium. It's like, 25 years since we are in this next 1,000 years, and it's pretty exciting. We could have died to like some atomic bomb, we could have died to a plague, we could have been consumed by some runaway artificial intelligence, but luckily, so far, this hasn't happened. So, okay, and to celebrate, we actually are going to do something pretty special and pretty unusual today. So, in the morning, I was thinking about what topic should we be covering today, and I thought that, hey, we might cover Grid Scrubber, that process which tries to detect latent failures in disk. So, to not let data just rot there, you periodically go and read the data, and if it is corrupted, it is repaired. But sometime in the middle of the day, I got an interesting question into my head of what happens if I run Beetle cluster on TMPFS? And I kind of tried to run it, and the results were surprising, and I started to dig in it, and I was thinking, oh no, I really want to dig deep into the phenomenon I'm observing, but I have a stream in 10 minutes, and no way I will be able to investigate this. And then it dawned on me that, hey, actually, I'm not going to cover the scrub at all. I'm just going to cover that exciting finding I did today. Okay, so let's get started. And apologize, it is unscripted Twitch stream. I'm not preparing. I always rambling. I'm forgetting things. It's always super messy. Today is going to be double plus messy because I will try to debug a problem I'm seeing, and so there's probably be a lot of me doing stupid things. So with due apologies given, let's get started. Okay, so what is that experiment I'm talking about? the experiment is pretty simple. I'm going to run target under extreme conditions. And there are like two parts to the conditions being extreme. One is that I'm going to run it on top of really, really fast hard drive, which is actually not a hard drive at all, but rather main memory. And second, I'm going to run it with, like, very small batches. So our overall theory of performance in target is that, like, we always batch work. We, like, aggregate many individual transfers into like huge packets of 8,000 transfers, and then we do complicated work once for an entire batch, and that's why we are fast. But we also should not be too slow if we are getting, like, individual transfers. And that's what we're going to do today. So we aren't going to, like, send normal batches. We'll be sending individual transfers. Okay, let's get started. So first of all, let's open our terminal. And let's go to our technical directory and see our benchmark. The benchmark I'll be running on Linux machine, not on Mac, because I kind of like, I suspect that it has a lot to do with I/O ring and like specific operating system interfaces. So I don't want to debug like Mac problems, because for Target Linux is a more important deployment platform. So this is the code which is going to run on Linux. It is a script which I implemented in JavaScript because, like, I like to have better support for synchrony and better code completion in my bash scripts. And it's like, really pretty simple. We'll be working in the /tmp directory, and on my Linux machine, /tmp is tmpfs. So it's not actually backed by hard drive. It is backed by random access memory. And I'm going to run a cluster of 6 replicas. So first of all, I will format in parallel all 6 data files. And then I'm going to start each individual replica, redirecting its standard error to a log file. And then I'm going to run benchmark. And that's it. So let's actually go and run it on my Linux machine, which I'm going to SSH into. And I kind of like have this kind of a curious, curious way of running things. So let me explain what's going on here. So I'm running 2 scripts on the left. RS, which stands for remote sync, and RR, which stands not for reverse debugging or whatever, but rather for reverse run, but rather for remote run. So RS is simple. It is just an rsync script, which scripts my PTB work directory to a corresponding directory on my Linux machine. So on the right, there is like Linux terminal, and you see here that the context here is exactly the same as I have on the left. And then I go and remotely run this make file, which means that I actually go and run this make TS on this machine. Okay, and not showing the screen. That is embarrassing, and I always count on you, my dear viewers, to to point out when I'm like being especially embarrassed. Again, like, truth to be told, I said that I'm going to be like super messy than usual, but like, not to the extent of not showing the screen. Okay, so let's go quickly through it. Again, so this is the script which we are going to run to launch the benchmark. It's pretty simple. We have 6 replica cluster. For each replica, we format the data file, and then we start a replica, and then we hit it with the load. And by the way, like this is a really powerful thing. we don't have a separate benchmark program to generate the load. Our benchmark load, standard load, is just encoded into our binary. And that makes this sort of investigations much, much easier because, well, if you have a tag bit or binary, you could always hit it with the benchmark. And then, let's do this again. What I'm running is this like sequence of commands. I rsync the current directory between my host machine and my Linux machine where I'm actually running the benchmark. I kill any leftover target and zig processes on remote machine. And on remote machine, I run this make script. Because make ts is air-synced between two machines, I essentially run that thing on that Linux machine. And okay, so we are seeing that our benchmark is running. And let's see the results. This is not what I was seeing earlier today, perhaps. This is much better. Like there isn't a problem here. Okay, what's going on? Okay, let's do this again. It should fail because if because if it doesn't fail, like I wouldn't be able. Okay, yeah, now I'm seeing the problem. Okay, so you see on the left, like we are running the benchmark, and on the right we are looking at the log of one replica, and kind of like you see, like there's something wrong here. Like it says like, hey, like there was like no machine prepares, and now it is like ignoring too far ahead, and something's basically off here. Like like replica is ignoring prepares. Like what's going on? It shouldn't be happening. Okay, so let's I guess let's maybe try to okay view it full screen. So we have this log. So yeah, this is the log of replica 0. And when I run this benchmark, I've already checked it. The benchmark runs in view 1. So replica 0 is actually the last replica in the replication ring. And you see that what happens here is that replica fails to write a prepare because it is waiting for input-output operation. So as a reminder, in TagEbital, everything is limited. In particular, we have a compile time limit on the number of concurrent disk operations, which could be in flight at any given point in time. So if a replica receives a prepare, and there isn't an available IO operation for this prepare, it is not going to get written to disk. And here we see that this is happening a lot. So you see, like, this replica misses a lot of prepares. And this is pretty bad because this means that replica just, like, forgets about those prepares. And then by the time it needs to commit them, it has to repair them. And that this causes, like, the replica to fall behind and ultimately, like, trigger state sync. So you see, like, here, like, we are failing to write some prepares to disk. And then, no machine prepare. We are failing to find a prepare locally for committing. And then after some time, so like, here we are unable to make progress committing. And okay, yeah. And now what happens is that we are stuck committing, but the cluster progresses ahead. And it sends us prepares which we cannot append to our journal because everything has a limit. And our write-ahead log also has a limit. It only has 1,000 slots in it. So if we are on a particular checkpoint, we could only accept 1,000 prepares in the future. And here the cluster is on OP 7000 something, and we are on OP I think 2000 something, and our prepare max, the end of our log is about 3000. So the cluster is very ahead, and we've fallen behind. So it's kind of understandable why we are falling behind here, because and this is counterintuitively, we are running on TMPFS. So actually, there is no any kind of back pressure on the primary to wait for stuff to get written. It basically prepares at the speed of memcopy. And kind of hand waving, that is why the last replica falls behind, because everything is so fast, including the primary, that it can just flood the messages. But still, it would be interesting to understand, what causes this that, because the primary is able to process this volume of repairs. So why wouldn't our backup be able to do so? And I did some debugging. So we wouldn't be debugging this from the start. Rather, we'll be debugging it from the place where I got stuck. And I've traced this to a particular lone CPU stall. So let's actually, okay, let me just show this. So I will go into our storage, and I will go into the loop which executes next tick callbacks. So remember, in Tagabital we have this next tick machinery where if an asynchronous function, okay, zoom. Yes, it is different one. So let's say font size. Let's say it's 20. 22 is a little bit too small. 24. Okay, yeah. Now should be better. Okay. So we have our next tick machinery. When asynchronous function, a function which takes a callback, is actually able to complete the work immediately, we cannot just invoke the callback, because that runs the risk of either overflowing the stack or violating some invariance. So instead, we want to push callback onto the queue of the message, onto some queue, and then get back to this queue at the end of the event loop turn. And this is essentially this end of the event loop turn here. And here I'm going to print every time when it takes a long time for us to execute the callback. And this is how I do it. So I'm creating a T, which is our debug timing function, and I say at the end, print if longer than, let's call it 8 milliseconds, next tick. Okay, and let's go back to, okay, no. Yes, I do want to close this terminal. Let's start running this thing. While it's compiling, let's look at what we've done here. So this is really simple debug utility, which I like to have in any given project, which allows me to quickly time sections of code. So inside this timing thing, we store a timer which tracks elapsed time naturally, and if the elapsed time is bigger than our threshold, which we've passed in, which is 8 milliseconds, we are going to print something. Well, we're going to print how long did it took. And yeah, sadly, today we'll get to get patient, because yeah, Zig still use an LLVM, so compiling with optimizations takes a lot of time, and it's going to be, I guess, roughly a minute between each of our iterations, which kind of like really is unfortunate. Param, 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 param. Okay, I hope. Okay, yeah. Now it is finished. Okay, and now let's see. Let's wait for the benchmark to start properly. Once we see, the batches coming in. Okay, and actually, why do less? Let's do more and grab footage. Okay, so you see that, like, every once in a while, we get this next callback, which takes more than 10 milliseconds. And this is like just a CPU work. So you see, like, there is no kind of any asynchrony here. Just like invoke the thing and then print the time. So it is 10 milliseconds of CPU work. And obviously, during these 10 milliseconds, you are not able to process any kind of messages. And most of our messages take less than a millisecond to process. So that means that while we are in one of those styles, we could accumulate a lot of messages in our buffer, like in kernel, because our messages are also like very small. There is like only like two transfers per message, and that's why when we return from the stall, we realize that, hey, we have like a whole bunch of prepares and we cannot process them at the same time. And to be fair, this also is happening on the primary. So one is a primary, and actually, it seems like primary is maybe even stalling a little bit more. But the primary is a primary. Like if the primary stalls, like no one, everyone waits for it. But if you stall, primary isn't going to wait for you. So this is what I want to debug today. I want to figure out like who exactly is stalling here. Okay, and while we are doing this, let me put another let me put another printout here. Let's call it 6 milliseconds. Okay, because I think I've actually traced the thing to that particular function which I've instrumented, but let's double check. But yeah, anyway, so the theory is this. The theory is that like something in our database periodically takes 10 milliseconds to process, while a backup is processing this for 10 milliseconds. It gets like a backlog of messages. So by the time it finishes processing, it has to deal with this entire packet of messages. But it so happens that due to limits to amount of on-disk concurrency, it has to drop some of those messages to the floor, and which in turn creates more work for this replica, which leads it to fall behind. Now, what is surprising here? If actually all our messages were full, if all our messages were like 8,000 transfers, then the work we do at the end of the bar would have to process like 500,000 transfers. And that, like, although we try to smooth out latency there, like, there I probably would have expected to see like some lag. But here we are processing tiny batches. And I don't think tiny batches should be this long to process. Like, just there's almost no data. It should be faster. Maybe I'm wrong, but I'm like, at this point, I'm curious. So let's see. Okay. I am not. I'm not getting this. I was sure that. Okay, so. Okay, this is something fun. So if we look at the first replica, it hits my latest printout. Can I? Okay, yeah. But other replicas? Okay, this is curious. So actually, maybe this is something else, because replica 4, 5, and 0 don't get to this. Or maybe they actually don't get to checkpoint at all. Okay, so. Okay, so maybe I'm not seeing this printout on the last replica because it just doesn't get to the checkpoint because it falls behind before that. And it's actually like maybe it doesn't matter because maybe the backlog propagates. If the replica before the last one gets a stall and gets a bunch of messages, then all those messages are going to get sent to the next replica. So it will also, even if itself is not stolen at that moment, it will still see a batch. Okay, well, anyway, maybe it is true, maybe it is not true, but I'm still like super curious about like what makes the primary stall here. Okay, so let's see what do we got in our checkpoint. So we have some. Okay, we have a bunch of functions. So let's just trace them all. And okay, so this here actually, let's call it 7 milliseconds. And let's see if anything here takes more than 4 milliseconds. So let's copy this and let's see. Insert only pairing. I'm just going to stupidly manually trace everything, which could be the problem. And then we'll see. Grid scrubber checkpoint. Okay, so that is the thing I wanted to talk about, and it would be fine if actually it is the scrubber in the end, but probably not its state machine. A state machine, client sessions. Wait, when I did state machine, yeah, I actually want to save it as a state machine and not a scrubber, otherwise it would be mightily confusing. Okay, then we have client replies. And finally greet. Checkpoint. Okay, so let's see which of you has done that, the lords. Okay, let's see who is to blame. And yeah, I kind of like, I'm kind of like feel like a caveman here, like, just go in and manually add in those printouts for long spans of times. And like, I wish I like, knew some magic thing like which allowed me to immediately like see what is slow, but sadly I don't know. So my usual tool for like, first level assessment of what might be slow, like finding a hotspot, is perf for Windows, for Linux. But perf is a sampling profiler. So the way this works is periodically, like, every like maybe 200 microseconds or something, your program is stopped. And then perf is going to see what is the call stack at that point in time. And like, it's going to write this call stack in some sort of a log file. So after the run of your program, you get a lot of samples of call stacks of your program. And this is excellent for figuring out which functions take a long time on average. So like, if 50%, like if you want to find which function contributes like 50% of execution time of your program, then like this approach is really good. But here it is not it. Like that function, which takes 10 milliseconds, like, we actually call it like very infrequently. So it doesn't account for a large fraction of execution time. And still I want to find it. And I don't like, I don't have like a ready tool which I can just use here. Like, like in theory, I should use some like tracing profiling, or as I recently learned, there's like this called Intel process tracing, which like in theory solves it. But well, yeah, I don't know this tool right now. Maybe instead of like doing this like the old way, I should go and learn something. But okay, let's try to brute force it. Okay, so let's see. Okay, so it looks like it might be agreed. It looks like, well, it's grid and something else. It's kind of, okay. Just kind of like I'm using that. Well, actually, why do I even print this if longer than if I could just print this always? So let's see. So in the state machine, I just want to print it, and in the storage, no, in the storage, I don't want to print it, otherwise it will spam. Checkpoint trailer, also want to print client replies, want to print client sessions, want to print Actually, I think all those things I just want to print. Apply to workspace. Okay, so let's try to rerun it. But for now, okay, so uh, grid is grid checkpoint grid is definitely a suspect. Why it takes 5 milliseconds to checkpoint the grid? Okay. Ha ha ha. Ha 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 ha. Let's see. Okay. Oh. Actually, let's do this. So this time I actually can print several times. So we could say here tprint grid preset stuff, and here we can say grid the rest. And okay, so for preset we do include staging, exclude staging, and cut chunks. Okay, okay. I got a feeling that this might be this. That this might be. Okay. 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 So maybe print and commit checkpoint data. If longer than let's keep it here. Okay, but hopefully we'll see. Okay, let's see 8 point something. No. How do I 8 point? Okay, yeah. Okay, so grid encode chunks, next tick. Okay. Okay. Yeah. Well, we'll have to wait it, but okay. It kind of like feels like this include stage and exclude stage and could be the problem. Because it does a union for all bit sets. And I'm wondering if we could optimize this. I wonder if we could track, like, the highest set or like, okay, yeah, maybe not. Okay, let's see our new data, which hopefully should be clearer. Okay, and let's well, yeah, okay. it is preset stuff. So preset stuff takes some large number of milliseconds. Okay, let's look at the preset stuff. Can we somehow make this faster and like what actually takes time here. So include staging. Going to toggle oh well, it's already pretty fast. Actually, are we using anything here besides this thing? Okay, well, let's do some bigger timing. Okay, temp print include staging. And let's move this to the end. Exclude staging. Encode chunks. Okay, no, these are actually encoders, so they like, I don't believe this encode chunks actually encodes anything. Or maybe yes. Okay, what happens here? So preset encode chunks returns encoder, which is a streaming encoder. Freeze chunks. Oh, okay. Let's just print it. Encode chunks. Exclude staging, and here, what are we doing? Let's call it some chunks. Okay. But I get the feeling that this is going to be include staging, exclude staging. Or maybe, okay, reset checkpoints. Okay, so encode chunks, like this one should be okay, so this one right here is linear. So I guess, yeah, I guess what we are seeing here is that free set is kind of slow. So as a reminder, free set is a bit set for our is the bit set of like free and allocated grid blocks for our entire grid. Actually, I'm wondering like how long is our free set? So let's print grid free set. Blocks. Do we have word count here? Like how many? Well, okay, let's just print this. Bit length 64 length. Okay. Uh, all the while our data is ready. So let's see. Okay. Okay, so this is okay, this is interesting. So the whole thing is 8 milliseconds. Exclude staging is 2. Include staging is 2. Where are the rest? Okay. Okay, it doesn't. Honestly, it sort of doesn't make sense. So include 2 milliseconds, then encoding is trivial. Some chunks is also like half a millisecond. Then, but why? Why do you accumulate 8 milliseconds here? Okay, something's not right here. Okay, let's double check this. So each print resets the timer so far, and that's why I'm like seeing the differences between the two. So to get the total, like I mean, ideally, like there would be some API on timer to get me this, but I don't think there is. And rather than adding it, I'm just adding the second timer. Okay. Okay, replica. Still it is. Okay. It is kind of like surprising. So, so I don't want to print the masks. I want to print the lint length. Okay, so it sort of feels like 4 milliseconds are getting lost here somewhere. So like you see how it is like 12 milliseconds here, but kind of like this only adds up to like maybe 9. So we are, there's something else. So grid total. Yeah, yeah. It's actually interesting. So maybe. Okay, so actually this means that it's not only reset. There is something else internally here. Okay, and before oh, hey Chaitanya. Okay, apparently there is a pull request which gets rid of that slow thing, which would be very excellent indeed. I mean, like, what is this? Can't you? I mean, the computers, like, I mean, it doesn't work. Okay. Uh, this is horrible. This is worse than Linux. It shouldn't be working that way. Free grid blocks when checkpoint becomes durable. Let's see. Free sets. Yeah, okay, there again. Yeah, okay, it's exciting, but yeah, Chaitanya, if you are listening here, yeah, it would be good to check that we are not actually too slow on the CPU time because yeah, like there is like 8 seconds of CPU, and actually, how large is our free set? So our free set is like about half a million ints, which is like a lot. I'm wondering if we could also do something stupid there, like tracking, um, basically tracking the largest bit allocated, because I would expect that for like most of the data files are going to be small, so like you shouldn't actually like traverse your entire free set. It would be enough to like traverse like only like part of it. Okay. I'm wondering if like there is also some quick hacks we can do here. Okay, but let's chase the rest of it. So like 5745 is the grid total, but commit checkpoint data is still bigger than this. Okay, let's go back to our commit checkpoint data. What could it be? Could we be doing some like horrible login here or something like that? Okay, so let's double check that I'm not missing anything here. New untitled text file. What is this? Include staging. Grid total. Okay. Wait. Oh, yeah, it was a mistake to include columns there. So let's see. Okay. So am I missing something? Or who are milliseconds here? So include staging, exclude staging. That matches grid total, but that doesn't match commit checkpoint data. Okay, so there is one more suspect here. There is definitely someone else who is making stuff slow. Okay, let's double check that we logged everything. And certainly repairing is being logged. And code chunks is being logged. And code is being logged. And by the way, just to double check, I am logging them with deferrers, because if you forget a defer, well, I don't think hook is doing anything here, but well, okay, let's print hook if for any reason it is send commit cannot, like send commit definitely shouldn't be blocking, but okay, I mean, let's be paranoid. Commit checkpoint data, yes, and we are running without append-only file, that is for sure. So scrubber prints state machine prints client session prints client reply prints. Okay, could it be this log? I mean, this couldn't be logs, right? RTL time it print logs. Okay. Uh, let's see. What's going on here? Well, I guess like one super quick fix here would be to remove those include stage and exclude station functions and just fold them into encoder, because like we really shouldn't be writing to that memory. Okay. Okay, let's see now. Assert on the repairing. Okay, I clearly don't understand this. Something's missing here. Okay, let's see the next one. Commit checkpoint data. Okay, maybe I messed up my internal login, but okay, yeah, I feel like I need to I feel like I need to meditate on this a little bit. But we've definitely identified. Actually, okay, let's actually do this like real quick. Let's remove include staging. Let's remove exclude staging. Let's also remove those prints. And leave only like the total one. And instead, when we encode chunks, we actually, let's see how include staging. Okay, and source words. Okay, so let's do this like really quick. Source words 2. Okay, and source words 2 the same. And where are we using source words? Oh, Okay, so let's try to see something for E. Okay, yeah, it's slightly. So I was, yeah. So basically, I was going to like quickly check that, like, if we just like pass 2 slices into the encoder, will it be able to like do on the fly zipping? But there is some mem copies here, and I feel like I'm like just too tired to like not mess up. So I'll leave this for the next time. But yeah, hopefully this like live debugging of performance problems was interesting. And if you want to see more of that, then please join with us next Friday at 5 p.m. UTC, where we either will be chasing down this tail down to its rabbit hole, or maybe we actually go and take a look at the Scrubber. Thanks for joining today, and goodbye.